welcome everyone. It's my pleasure to introduce today our fourth webinar about the use cases developed throughout the European project EECONE. So EECONE is origin is based on the fact that the global e-waste worldwide is growing every year more and more, reaching 62 billions of kilograms in 2022, reported from the last e-waste global monitor. So it's a very important quantity of waste, even per capita. And what is very, very important is that most of this waste is actually not very well recycled. And therefore, there is a huge need to implement some strategies in order to prevent all this waste to end in the landfill or things like that. For this reason, the EECONE project has been developed, has been proposed, and has received a grant from the European Commission. And we develop a technology for zero waste future of electronics components and systems. As you can see on the left, the EECONE project is targeting circular options strategies in order to maintain the residual value of electronics in the value chain. And for this, we have selected 6 key circular options, which are reduce, reliability, repair, reuse, refurbish, and recycle. And we try to work designing, manufacturing, and extend the useful lifetime of the electronic products throughout these circular options. We are working on 4 key objectives, which are to define green electronic components and systems, also to make those components and systems more as green as possible, not only from a greenwashing point of view, but actually trying to implement innovative design solutions as well as manufacturing techniques. All this work is developed in the frame of several use cases. And in the previous webinars, we have started to present those use cases. And today, we are going to see the 3 last use cases that will be presented throughout our webinars. The reason why we do this is because one key contribution of EECONE project is also to develop and to build this consciousness around circularity and eco-design in electronics and system components and systems. We want to clearly empower the community around these 6R strategies and eco-design. So today, we are going to listen to 3 use cases that are currently under development throughout the EECONE project. First of all, we will have Thomas Ewald from BOSCH, who will speak about from waste to worth strategies for sustainable PCB and component reuse in automotive applications. Then we will continue with Christian Rein from Danish Technical Institute, who will present inks for robust and sustainable electronics. And we will conclude this webinar with Merck Tetik from BECO, formerly ARCELIK, presenting the creation of critical raw material value chain, traceability, system, and recycling strategies in appliances. So before giving the word to Thomas, I just want to mention also that in addition to these webinar activities, we are currently, and actually it is this week, we are currently running a summer school here in Grenoble in the frame of EECONE project. This summer school is dedicated to ramp up the community in terms of knowledge related to eco-design and circularity in electronics. So it's very, I hope we will be able to report in a future webinar about this event. And without wasting more time, I give the word to Thomas to present his use case during this webinar. Thomas, the floor is yours.
Thank you, Jean-Christophe. I think you all can hear me. I'm going to share my screen. So now you should also see my slides. Is this correct?
Yes.
All right, so then let's start. Now, as Jean-Christophe already mentioned, I'm going to introduce use case 1 from waste to worth strategies for sustainable PCB and component reuse in automotive electronics. My name is Thomas Ewald from Robert Bosch GmbH, and in this use case, we have also other partners. We're not alone, so this is done together with AT&S, as you can see here in the lower side of the slide, with Infineon, with Bosch Portugal, Bosch Hungary, and Bosch Germany, and also the Fraunhofer IZM from Berlin. So many people are involved in this use case, and the focus in a nutshell is less e-waste in automotive applications with focus on IPC class 3. And we will focus in this use case on 2 R's, on reduce and reuse. So for the reduce side, it's about less e-waste by the usage of thinner substrate materials with less material, thinner copper foils, less galvanic copper, and recyclable substrate materials. And with regard to reuse, we try to reuse components and press fit connectors. So this is the target and focus of use case 1. And from content side, it's clustered in 4 different activities, which you can see on this slide. For each activity, you also see the team means which partners are involved in the use case activity. So first is reuse of components. Here it's really about, as already mentioned, reduction of e-waste by the reuse of components. We will come in detail to all 4 in the next slides, but here just a brief overview. The second is sustainable PCB. So here is the focus to decrease the product carbon footprint and to reduce the e-waste. And then the third one, reuse of press fit connectors. As you can read by yourself, reuse of pins and PCBs for less e-waste. And last but not least, sustainable system in packages and interposer technology, where we explore options to increase the sustainability also in this field. So all about assembly and interconnect technology with focus on automotive electronics. So then let's directly jump in the first activity. It's the reuse of components. And here, as already mentioned, the target is to de- and resoldering components, and we choose a BGA component from a radar ECU from Bosch, and the BGA is from Infineon. And the target is to be able to de- and resolder it without losing reliability. And at the moment, we developed a profile for de- and resoldering at the rework station. This was very tricky. It took a lot of time, but meanwhile, it works. And we eliminated all the failures. There were a lot of challenges like solder squeeze out because you have to apply some pressure and so on and so on. And now the next step is to do reliability tests with this de- and resoldered BGAs, and also to calculate the product carbon footprint for this situation. So in the right upper side, you can see a very nice explosion build up from the radar ECU which we are using. And here you can see on the lower side the top view and bottom view of the BGA which we are investigating. On the left side you see our test board where these BGAs are mounted and then tested. And here on the right side you see a Weibull plot where the investigation was done. What is the impact of several time reflows? Because if we talk about reuse of components, we will have more than 3 times reflow soldering process. and normally components are only released for 3 times. And then the first question, of course, was what will happen for the reliability when we do more than 3 times reflow, and luckily it turns out that there's nearly no impact, and now we are looking forward for the reliability tests of the de- and resoldered BGAs. So that's in a nutshell what is going on in the first activity about reuse of components. In the second activity about sustainable PCB. Here's the target, the sustainable automotive PCB, IPC class 3, with decreased product carbon footprint and less e-waste. And here we choose a high performance compute ECU to build a demonstrator with a sustainable PCB. So focus is clearly on PCB, not on the ECU. And this sustainable PCB in detail is that first we made it thinner, so we reduced the thickness of the FR4 material. Second is that we introduced recyclable material, which was very new, introduced in the market by Schengi. And third one is to apply less copper by using thinner copper foils. And the fourth one is a bit innovative. This is to use less galvanic copper, because this is by far the most energy consuming process in the PCB manufacturing. And if we would be able to use less galvanic copper, then we would be able to reduce a lot of energy consumption, and this would be very good for the product carbon footprint. All go along with some challenges for reliability aspects, and this is what will be now investigated in depth. So the demonstrators are already built and already tested, and now we're waiting for the evaluation of the results. And hopefully we will find out that it works very nice and smoothly with this sustainable PCB measures. Another aspect is to calculate the product carbon footprint benefits from this sustainable PCB, which is done at the moment by Fraunhofer IZM, so that we have in the end really also a kind of quantitative proof how much we improve with regard to product carbon footprint and also to e-waste. Then we have the third field or activity in use case 1. This is reuse of press fit technology. This we started this year, and so the test program is still ongoing. We choose 4 different pin types and investigate now various scenarios, like the reuse of PCB with new press fit pins, reuse of press fit pins in new PCBs, and reuse press fit pins and PCB both. And first target is now to figure out which combinations are possible and which not. And then we will see what are the next steps. So the investigations at the moment are done with single pins. So of course, at the end, we also want to have a validation of the results with a full connector in the PCB, because this is how it is normally used then in the product. And last but not least, we are also looking in the field of sustainable system in packages and interposer technology. And here also we want to try to make this technology more sustainable. So the first one is the reuse of SIP and interposers. So for interposers, we discarded it because this is not a real business case when you have to remove all the components, the solder, the copper, and then to reuse the interposer again. This doesn't make sense from a business point of view, but what might be interesting and what we are looking at is the reuse of the whole SIP module. This is a bit similar like the BGA reuse of components, where you remove the balls and reball it again, and then you can use it again. Another very obvious thing is to investigate how thin can the interposer of a SIP be. So the same like in the PCB, because if you make it thinner, then you save material, and less material means less product carbon footprint and less e-waste. And here we are investigating what are the lower limits, because warpage will be an issue then at some point in time. And also IZM, Fraunhofer in Berlin is calculating the life cycle assessment of these thinner interposers. And last but not least, we are also looking in the field of other technologies which are really out of the box for automotive applications, like glass substrates. They have many advantages, but also some challenges with regard to reliability. And here we are doing a kind of screening of the market and trying to see if there's some innovative ideas with regard to sustainability. So that's in 11 minutes, in a nutshell, what is going on in use case 1. So feel free to ask questions.
So yes, I just mentioned in the chat that we keep the question for the end of the presentation. So please, if you can place your questions and remarks in the chat, then we will ask the presenters to answer your questions. So thank you, Thomas. And now let's switch to Christian.
Thank you very much. I'll start sharing. Can you see my slides?
Yes, perfect.
Perfect. So my name is Christian Rein. I'm a product manager here at Danish Technological Institute, where we are developing new technologies for all industry. And I'm the coordinator for use case 3 here in EECONE, and I will use that as a framework for talking about inks, robust inks and sustainable inks for electronics. And the very foundation for what these inks can be used for is found in what's called printed electronics. This is a bit different from the traditional PCB-based electronics, where we now look at more at additive manufacturing. So thus we're lowering the overall waste by only adding the material that is needed. It gives us some flexibility regarding the substrates and also what kind of materials we can implement. And the environmental impact is also expected to be much lower, but still it's depending on what kind of materials and substrates and processes that is included. So that's something that needs to be taken into account. This printed electronics has already been shown to integrate sensors, antennas, batteries, etc., making it more and more versatile as time progresses. And it gives some new design freedoms where you can customize the shapes, the forms, and creating an overall more lightweight electronic system. And the use case that we have here in EECONE is what we call membrane switches, which is normally produced by the Danish company Melsontech. And we are collaborating with Cynano, that is producing the carbon inks for this design. And we are developing conductive inks for this use case. Normally, these membrane switches, also known as keyboards, is meant to be used in harsh environments where they use as input for operators operating machinery. And the system overall is a multi-layered system of plastic that can be attached on the surface, and is currently using silver as the conductive tracks. Carbon is derived from fossil-based fuels, where you are then using the carbon layers to provide mechanical or friction resistance on certain areas of the electronics that otherwise would lower the lifetime of the overall electronics. So in use case 3, we'll try to improve these membrane switches through the 6R strategy. This involves reducing the environmental impact and its vulnerability to environmental conditions, hoping that we can increase the lifetime. And it requires us to look at the very material composition of the inks used in producing these membrane switches. This also includes the use of eco-design in order to optimize the overall composition and choice of materials. Let's see if we can go on. Yes. The inks are normally determined by a combination of various components. There are the fillers that provide the overall functionality of the ink. This, for conductive ink, would of course be conductive materials. This could be copper microparticles, silver nanoparticles, silver flakes, or carbon nanotubes, mixed up in a solvent, a carrier for these filler materials that can also have the rheology or drying behavior modification of the overall ink. The binder, providing the adhesion between the material and to the substrate, which is very important when you're doing this printing. And then we often also look at the rheology control and stabilizing in order to make sure that the printing process and the lifetime of the ink itself can last as expected. As you can see here in this scanning electron microscope, you have a agglomeration of particles. Some of them are surface passivated, for example, to provide the right stabilization. All of this is mixed into the ink, as you can see in the picture. These inks, depending on the methods of deposition, needs to be accounting for several parameters. If you are taking, for example, screen printing, which is a very robust, established method for printing electronics, then you need to take into account the mesh size. As you can see in the picture, the mesh through which you put the ink is made up of a lot of pores through which the material has to go through. It also depends on viscosity and stability. And for example, for inkjet, you would also take into account density and surface tension in order to have the right flow dynamic. Then there would also be a similar consideration if you're doing roll-to-roll production for upscaled production. So when you're looking at the printing, here we're showing with the copper ink that we had in the picture before. We are applying it to the print screen, flooding the screen, and then afterwards we have it on top of the substrate, the plastic, for example, where we are then squeezing down the material to create the printed tracks, as you can see in the middle image. After this printing is done, you need to remove the solvent again. Now just going through the hassle of mixing everything in, you need to take out a lot of the organic material out, otherwise you're just blocking the conductivity. And through that, you would first evaporate through the curing, and then you put it through a post-processing step of sintering. For example, copper inks, you need to make sure that the copper particles are being fused together through this sintering process in order to provide the macro scale conductivity throughout the entire length of the electronics. We often use a 1,000 square standard test grid, as you can see in the last image, in order to validate the conductivity. There's also other ways of validating the quality of these inks, is also to make sure that it can withstand the adhesion and mechanical stress. Otherwise, it's a little use if it just flakes off. So we are applying, for example, crosshatch testing, where we're scraping and brushing and trying to peel off the material after we have deposited it. And based on that, we can also get an idea of the application worthiness for electronic. We also look at, for robust inks, it needs to be able to withstand a lifetime of use. For example, these membrane switches should be lasting several years in a harsh environment. And for that, we need to have the electronic powered used while we are cycling the humidity and temperature environmental chambers. And then follow that, if we are investigating the failure mode, what went wrong, how can we improve the design and make sure that the electronic lasts longer. Electronics that last longer is also electronics that you do not throw out, thus reducing the waste. And one of the questions that sometimes can be met when you are trying to suggesting a new material to include is, well, why didn't status quo work? Right now, a lot of silver is being used in printed electronics since it was a standard that's been used, silver flakes. But one of the things that needs to be taken into account is the very high climate change potential, also all environmental impact that using silver, for example, have in comparison with copper. Shifting from silver to copper reduces the overall environmental footprint by 96.5%. Thus, there's a very large driving force to move into the copper particle regime instead. This is what we have been focusing on in EECONE. And in this project, we are looking at the other aspects as well. For example, there's also the aspect of the silvers not being also being used in a lot of key technologies. So there's a danger, so to say, that silver is a scarce resource. And then there's also that silver price is also a driving factor. When you're looking at the bulk materials, copper has a lower overall price compared to silver. So that's also an industrial interest if we can nail down the right ink formulation in order to introduce copper inks instead of silver. And some of the tools that we're using through this overall redesign of materials and electronics is safe and sustainable by design methodologies, life cycle assessment, but also the eco-design tools that's been developed. There's some also here in EECONE. And it allows us to get a better track of what kind of materials that can be put together and what the benefits would be. One of the ideas is that we could look at a more circular system for materials, where normally we take the particles extracted from primary resources, formulate those into copper inks, and then screen print them in order to create the copper electronics. After this shredding or the end of life, we would like to then leach out the elements, leach the copper, and then reform the copper particles from the copper salt in a resynthesis process as an alternative to the more non-circular end of life where we would have incineration or landfill. As already was introduced, these are some of the driving forces for moving to these kind of designs in electronic production. There's also all the European initiatives that needs to be considered when designing these inks. There is the consideration for nanomaterial effects, the hazardous materials that we could include or not include in ink formulations, as well as how to design this for recycling and easy extraction of the material in the end. There would also be tied into the new initiatives of sustainability products regulation and circular economy action plans that is also being drawn out. All of this is done together with the rest of the partners and institutes in EECONE, where we are trying to make the next step in sustainable electronics.
Thank you very much, Christian. So once again, do not hesitate to place remarks or questions in the chat box. And now let me introduce Mert for the last presentation.
Thank you. I will share now my screen.
Yes, it's okay.
Okay. So, hi everyone. I will today explain the use case 5 that I am leading with Kubra from Beko compressor plant in Turkey. We are trying to make a creation of critical raw materials for appliances, especially for now for compressor and refrigerator, and afterwards maybe other plants. I don't know for now. And we will also do creation of a traceability system with recycling strategies. So for now, let's switch to the first slide. So what's use case 5 all about? So it's all about bringing innovative solutions to the household appliance sector, especially when it comes to critical raw materials, and making the whole system more circular and sustainable. The main goal is to reduce the supply risk linked to these important materials by improving how we manage them throughout the product life cycle. And we will do it by firstly by building a stronger value chain around these critical materials. Then we will be putting the traceability system in place so we can always know where these materials are. And finally, by creating a better recycling strategies for electronic components. if we come to the question, what are we aiming to achieve? It's for better traceability of the critical materials in our appliances, more transparency across the supply chain, higher recycling rates, and smarter use of the valuable materials we can't afford to lose. We are planning to reach these goals by making everything more traceable and transparent systems. We will be using QR codes and barcodes to give you. Sorry, yes.
I think we lost the screen. You were mute for a second, and you don't share anymore the screen. Can you share it again?
Share again. Sorry.
Okay, perfect. Thanks. No problem.
Thank you for warning. Okay. So I will start from here. I already told that by reaching these goals, making everything more traceable and transparent, and improving how we recycle and reuse critical raw materials. We will also be using some smart technologies like smart tracking system. This is like QR codes and barcodes to give every electronic component its own material passport, so we can always know what is inside and where it came from. Data integration. It's all the players in the supply chain will be able to share information clearly and easily. That means better coordination and more trust. And the third one is recycling technologies. We are also developing new and more effective ways to recycle those high-value materials so we can get them back into the loop instead of losing them. So in practice, we will be gathering detailed info about the critical raw materials in the bill of materials, as known as BOM, a full list of what is inside of each household appliance. So as components coming from different suppliers, we will build a digital passport for the product, and this product is linked to the barcodes or QR codes placed on each electronic component. And so what does it mean? If you ask, it means when you can scan a component, you will instantly see what it's made of, and the quality of these materials, and even how it should be recycled. It is so if I need to shortly summarize, it is simple and trackable. It's a smart system. And here we will look at the structure behind use case 5, the roles and tasks within work package 2 and 3. So as BECO or responsibles are, we choose the refrigerator compressor as our focus device as the first home appliance because we are working there. Since our expertise is in compressors, we are concentrating on both the compressor themselves and the inverter cards that are used with this compressor, which is the PCB. First, we identify every component on the electronic cards. Then we started investigating what these components are made of, and we reached out to our purchasing team to collect material declaration forms from the component suppliers. Even deeper, we used an RF device to perform elemental analysis on the components. Finally, we sent our compressors and inverter cards to the recycling company, which is also working at EECONE project, to explore the possible recycling strategies. So for the second partner, the recycling, their role is focusing on developing recycling methods and applications for recovering critical raw materials from electronic components. They are working on innovative ways to recycle these parts. Together with BECO, as known as formerly as ARCELIK, they are creating a practical and actionable recycling strategies that can be applied in a real-world system. As for Özyeğin University, their focus is on developing a traceability software for tracking critical raw materials. They are working currently on work package 3 of EECONE, and including eco-design techniques. And they have also started integrating barcodes and QR codes directly into electronic components to support the traceability system. So let's take a closer look at EECONE's recycling strategies under work package 2. We got 3 key tasks guiding our work here. For the first task, it is repair and reuse. Firstly, we are looking into whether we can repair and reuse e-waste instead of recycling it right away. If it still works or can be fixed, we want to give it a second life. And the second task is recycling methods and material loops. This is a big one. We are creating a map of raw materials and e-waste and analyzing current recycling rates. Then we will define a priority matrix, basically figuring out which materials are most important to recover. We will also identify critical materials and combinations that can be recycled efficiently. Based on that, we will propose improved recycling methods for those materials. Also studying how to apply these solutions to both existing and new electronic components. And finally, for this task, we will map out critical raw material loops to keep materials circulating in the system instead of being lost in it. As the last task, we will overcoming recycling barriers. Here we are focusing on the challenges that prevent efficient recycling. The goal is to understand those barriers and use that insight to guide eco-design so future products are easier to recycle from the start. So here, let's talk about the goals we are aiming for and what will come next. First, the targets. We want to increase recycling revenue from PCBs by 300%. That's a major leap for us, and double the amount of recycled material, which is a full 100% increase, and boost the reuse rate of critical raw materials in electronic components by 50%. So as for what's coming in the future, after this project is wrapped up, we are not stopping. We have clear next steps for it. First is industrialization, and that means scaling up the technologies we have developed, getting them ready for real-world production. The second one is market deployment, which is launching these solutions into the global market. And the last one is expansion, which is taking this system and applying it across Beko's international factories. And the big picture is that we want to take the impact of EECONE even further, helping to drive global adaptation of this circular economy solution and making sustainability a core part of how the industry operates worldwide. And thank you for listening to me. That's all for use case 5.
Thank you very much, Mert. Thank you for the three of you. So it is now time open for questions. I checked on the chat. There is no much question at the moment, but I have some questions that I would like to ask to each of you. Thomas, in your presentation, you look after the reliability reduction due to multiple assembly cycles. Did you check about the characteristic evolution of the components that were submitted to several assembly cycles, thermal cycles?
I don't see Thomas in the meeting.
Yeah, I don't see Thomas either. Maybe he left. I don't know. This is surprising, or maybe he has a connection issue. Well, okay. Let's jump to Christian's. Meanwhile, we try to have Thomas back with us. Christian, I was wondering how your research activities are fitting to the objectives of the project in terms of circularity or environmental impact mitigations. Could you comment a little bit on this?
Yes. So one of the things we also have to acknowledge is that while copper is abundant on this planet and it's cheaper, then there is a problem about it being implemented in so many key technologies, and the limitation of copper, for example, being the availability of copper extraction processes in Europe. So as such, it's determined as a critical raw material, and as such, I think it's very important that we look at how to close the loop for things like copper. Also for many of the other elements, as I just said, silver would also be a very good point to see if we can close the loop on those elements. But yes, so one of the things we have looked into is within EECONE is to look at how we could integrate recycled copper in the copper reformulation or resynthesis in order to recreate the copper ink for electronic production. But it's something that still needs some development, I would say, because there is a risk of not having the right sizes of the copper when you are synthesizing compared to when you're just taking it directly from primary resources. And there is a balancing act of how much energy you're investing into the system, this circular system, versus how much you are saving of the material. So I would call it an energy mass balance. If you want to save, for example, some of these critical raw materials, these high value or strategic materials, you can invest a lot of energy in order to reform them with physical processes using a lot of energy in order to reshape them into a morphology that is better suited for high quality products. But if you want to also save energy, and there's a lot of focus on energy versus CO2 global warming, then there is a bit of a balance there. As therefore, I think it's very crucial that you have to do this eco-design in order to make sure that what you choose, what kind of route through the process is the best one.
Okay, thanks for this. But so regarding the ink that is not actually printed on the plastic substrate, is this one very easy to have it back in the loop? Because I guess you can get it back easily and recycle and reuse it, I would say.
So as far as I understand, we have collaborated with some recyclers in Europe, and there's some pros and cons. The traditional PCB-based electronics mainly uses copper. You normally shred it, then leach out with some strong acids, the copper materials, and then you can reform that to, for example, make the particles. Vice versa, you could also take that recycled copper and use that for galvanic processes in order to reform, for example, these recycled substrates as Thomas just presented. That would also lower the overall footprint. What some of the problems is that some of the recycling processes are pyrolytic. That means you're burning stuff. And here the PCB has a bit of a problem because it's often filled with a lot of glass fibers, which creates slags and which limits the amount of materials you can extract. So there's some pros and cons in these effects. And there, the print electronic would be much easier to go through a pyrolytic process. Also, if you're just taking a normal chemical method to extract the materials.
Okay, thank you. Okay, I will jump to Mert and ask you a few questions. Meanwhile, Thomas is trying to get back. So you have been working on your own specific manufacturing plants to develop this traceability and all these things. Would you say that this is easy to transfer to any kind of manufacturing plant for customer appliances, or would you say that there are some tricky things that needs to be considered?
Mm-hmm. So first, I think it's possible for other plants or other brands, for example, in white in household appliances. But I think firstly, they will need to do the same things like us, and they need to prepare a passport for the inverter board or electronic board in this case. And I think it will be possible in the future after we will make it expand to the other plants in Beko. And afterwards, I think it will be possible also to doing it in the other brands. Thank you for the question, by the way.
No problem. And actually, I have another question for you. So you mentioned that one of the EECONE partner involved in your use case is working on the traceability software for this for the product raw material description. How this is complementary to the perspective of the digital product passport that could be developed for the electronic products. Can you comment on this?
Recently, I made a meeting with the Özyeğin University, and they told me and they showed me something like an interface, and they have used how can I say, a machine learning system. And we also sent them a few examples for samples for inverter boards, and they trained their machine, and now it can detect which components are on the boards, both on the upside and the bottom side of the PCB. And it looks like it's possible at their side, but it's still not finished for now. They are still working on it.
Okay, thank you. I see that we have some remarks or some questions in the chat. So a remark about use case in agriculture. We have in EECONE, we have one use case which is linked to agriculture. It has been presented in one of the previous webinars. I recommend you to take a look to them to look for that use case. And there is another remark related to use case 9, which is not presented finally today. Yes, we will try to have that use case presented, but it has not been possible at last today. But we will try to place a video later on to present that last use case that was not presented today. So yes, Thomas, I think I see you are back. So let me ask you one or two questions. Yes, in fact, I was asking you a first question. I didn't realize that you were not with us anymore. I wanted to know if you look in your presentation, you present how you check the reliability reduction due to multiple thermal assembly cycles. I was wondering if you took a look to the evolution of the characteristics of the device itself, or if it was if there is any parameter, sensitive parameter that you could take a look to that in addition to the global reliability of the device.
Yeah, so sorry for that. I was my computer was frozen. I had to restart, and it took really long time till it was set again. So if we talk about reuse of components, where we and resolder it, and where I showed this Weibull plot, here actually we only do these tests on test boards. So not in a housing, not on a real PCB. It's just a test PCB, and the BGAs are not original BGAs. They are wired with something that is called daisy chain, where it's much easier to electrically measure if there is a failure.
Okay, so it's not the device itself; it's the PCB itself that is where you check the reliability.
Yeah, it's measured electrically if you have broken solder joints.
Okay. And I have another question. So you introduced this press fit technology that looks like a promising approach to remove and replace components. Do you think we could imagine that to have this TO220 made out of press fit terminals in the future to replace, for example, power devices easily once they are failing? What is your opinion about this?
Yeah, so if I would know it, we would not need to do the tests anymore. So this is one.
Do you have a personal?
Yeah. From my stomach feeling, I think it will be possible, but not in every combination. So what for sure will be possible that we can press in a PCB a pin and remove it, and maybe use a new pin and press it in the same PCB again. And this gives us then many degrees of freedom for repair in the line. especially when you have very expensive products with several PCBs stacked over another, and normally you throw away everything when you have a failure at the end of the line or in the line somewhere during manufacturing, and this would give us the degree of freedom to repair there.
Okay, thank you very much. Thank you to the three of you. Well, I think we are about to conclude this webinar. I would just like to make two short announcements. So during the fall period, before the end of 2025, we will run a second set of webinars to highlight the work done in EECONE to develop database tools and methods to support eco-design and design for circularity. So we will keep you posted on this. I would like to thank our presenters today. One of them was not available at last, but we will try to catch up with him and to make the presentation of his use case available later on. And I would like to thank also Crebier from INP-GRE for the organization of this webinar, as well as Arnaud Serra from Design and Reuse for handling all the logistics. I hope you found that webinar interesting, and I wish you all a nice end of the day, and see you next time to our EECONE webinars. Have a good day. Bye-bye, everyone.